So let us start with defining what is a signal. Okay, so we can say that a signal is a function that depends on one or more variables, or you can say independent variables such as time, then x, y, z, etc. Okay. So signal is a function that depends on one or more independent variables such as time, x coordinate, y coordinate, z coordinate. Examples: the output of a microphone. Okay, so the sound signals will be converted to electrical signal by the microphone, and if you look at a typical plot of this signal, the independent variable is time, and as you speak you will have this kind of variation. Okay. So this is the variation of voltage with respect to time. So here V of t is the voltage. So in general, the dependent variable could be any physical quantity such as voltage. In this example it was voltage. It could be current also. It could be, if you take the case of a picture, intensity. If you consider a thermometer, then temperature. Okay. Any of this physical quantity. Okay, it could be electric field. Okay, magnetic field, etc. So any of the physical quantity which varies with respect to some independent variable, which are time, position, etc. So this is the above example is and it is a one-dimensional signal, 1DC, because it depends only on one independent variable. Example 2, an image. If it is a black and white image, so it could be black and white or it could be color. Is an example of 2D signal. So if you look at an image, how do you plot it? You have x coordinate and you have y coordinate. So this is your x and this is your y, and you have some intensity variation here. So if you have some shape here, maybe something like this, okay, whatever, some picture is there, and you can see that the intensity at these portions, they are dark, okay, and some region it could be gray, some region it is very bright. So intensity is varying from position to position. Okay, usually in a digital or discrete time image, discrete time as well as digital. Okay, I will come into those once more again. Discrete time, discrete image means you will have everything divided into pixels. Okay, so different small regions, and each region will have some intensity. So that will define the picture. But if it is a continuous time, then for every x there is an intensity. So there are infinite number of points. But as you know, in a computer, if you want to represent an image, you can't have infinite number of points, say from 0 to 1 centimeter or something like that. Okay, so here you have a 2D signal because there are two dimensions or two independent variables which decides, or the intensity varies with those two independent variables, therefore we call it as 2D signal. Now what's the difference between a black and white and color signal or color image? In the case of a color image, so this is for black and white. In the case of color image, you have again x and y, but you have three things. So one is red, you have this component, and here I can write it as r as a function of x and y. So we have a red intensity, then with respect to x and y we have a green intensity, and also we have one more x and y. So this is blue. Okay, so let me use this color. I have blue intensity. Okay, so we have a red intensity, green intensity and blue intensity, and then together they represent a color signal. So at each point x and y, for example, if I consider this point, okay, so in every picture there is a corresponding point. This is a particular x and y, and what will be the color there is determined by a combination of the R value, G value and B value. So a color signal, so this is black and white, and if I say color signal, color image, it is having 3 components, and each component is a 2-dimensional dependence. Okay. So there is R, G and B. So in a color image, R, G, B depends on X and Y coordinate. Okay. Another example, a video signal. Example 3. It could be again black and white video signal, or it could be a color. So one more thing, let me say, since there are 3 components here, color image can be represented like a matrix or a column matrix. R as a function of X and Y, G as a function of X and Y. These are components. So this is the way mathematically you can represent a color signal. Whereas here, black and white, we will have I, intensity, grayscale as a function of time. How about color video signal? How do we represent or color black and white or black and white video signal? Is an example of 3D signal, 3 dimension. Why 3 dimension? Because you can treat a black and white video signal as an image which changes with time. So image it is actually a function of X and Y, but if you imagine there is a dependency on time also, then we have so a black and white video signal is a function of X, Y and T. So let me call it B. So B is a function of X, Y and T, where here B is the intensity of grayscale. Okay. Similarly, a color video signal is is also 3-dimensional, but has 3 components which may be represented as, so you have RGB, right? So you have R as a function of X, Y and T, green intensity as a function of X, Y and T, and blue color intensity as a function of X, Y. So this is the should change this to I itself, intensity. So this is red intensity, so red intensity varies with the coordinates as well as time, x coordinate, y coordinate and time. So this is green intensity and this is blue intensity. What else? Other example. So these are the most popular examples what I have seen, what I have shown. Similarly, voltages and current in a circuit you can think about. They are also functions of time. Then depending upon what signal that you have, we have different domains like 1D signal processing, like speech signal, it's a 1D signal. Then say ECG signal, they are also signals that varies with respect to time. EEG signal, so all these are examples of 1D signals, so that's a class of signals. And then we have 2D signals, which are mainly in electronics and communication. We deal with the images, so image signal processing. Okay, so that's another domain. And video signal processing is yet another domain. So those are the applications, those are the areas where we do it. And since we are using computers, we will have to discretize with respect to the independent variable and also discretize with respect to the dependent variable. That means intensities are discretized. For example, if you take an image, you can't have any value of intensity, you will have discrete allowed values. Okay, and so let me give you that example.
Sir,
Yes.
so what is grayscale, sir?
Grayscale is basically the degree of blackness. Like if it is completely black, we say it is one end of the grayscale, and completely white is another end of the grayscale. So between black and white, there is a range of value that it can have. So that degree of blackness, you can say. So between 0 and 1, if you say 0 is completely white and 1 is completely black, and then 0.5 is like a grayscale, 0.7 is another grayscale, but it is more toward dark.
Yes, sir.
Yeah.
Sir, also how this colors are arranged on the screen, sir? It's RGB.
Yeah. So let me take an example of an image. So
Yes.
mostly what we deal with in computers, they are digital signal, digital images. So let's look at an example of digital image. Digital image. So if you take an image, usually the size of the image is specified depending upon the number of pixels. So like you can divide the entire thing into pixels. Okay, so like this, and similarly you can okay, and then you can number them. One, let me use a different color. 1, 2, 3, 4, 5, like this. If it is a 256 by 256 pixels, so then this will be 256. And similarly you can number to this side also, 2, 3, 4, like this, and this will also be 256. So then we say that this is a 256 by 256. So usually we consider them in powers of 2. So width, but that is not absolutely necessary. that is more popular because of some advantage. So we divide the entire region, that is the x coordinate and y coordinate, which is spanning from say here 0 to say Lx, this is the length of the image, and then 0 to Ly, which is in the y direction. We divide it into different subdivisions, and then so you see that now a discrete element is something like this. You have one pixel. This is what is called as a pixel. Okay. Now to this pixel we give one single color. Okay, so that one single color, maybe, so here I have grayscale, so I give this color. Then I take another pixel somewhere here. Here I give another grayscale, maybe a more dark, like this. So this is another grayscale. So depending upon how many different grayscale, I am talking now only about black and white, so it will be having only one color, which is basically dark or bright. Another one I can give somewhere here. So here I will use maybe this. It is a more white color. So each pixel I am associating one colors, so that continues on for all the pixels. So there are 256 by 256 pixels, and to each pixel I am associating a different grayscale. So here I have only this 4 grayscale here in my pen, but if you have more, instead of 4, if you have say 256 grayscale, again you can have different shades of gray, different shades of gray. Now each of this gray scale could be represented with a code. Okay, so this is let me show you one more completely black, please. So here I have a black color, so I am this is a completely black. This is one extreme. So this I'm going to define it as say, so let me just show you a grayscale here. So this side I have complete black, and this side I have complete white. Like this, and then I have variations. Like this. Okay, I hope you can see this. So these are different, you can see different grayscales. So this is one grayscale, this is another, this is another. So each of this I can represent it with a code. This grayscale, if I have, so let me just put dot here, because so there could be many more scales in between. So I am putting dot here, and the code that I am assigning for this one is say 0000, 8-bit code. I am assigning all zeros, and here I am assigning all 8-bit 1. Okay, there are 8 bits and all 8 bits are 1, and this one is 0001 0000001, and the next one is 0 0 0, then 0 0 1 0. So like this. Next one is 0 0 0 0 0 0 1 1. So like this it goes. So this is grayscale level 0, then 1 2 3 dot 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 255. So usually 255 is a 0 to 255 is a common case. When you look at the paint, you draw something, usually you get it in this format. So each pixel will be defined by this one of the code corresponding to the grayscale. Okay, the how much dark it is or how much white it is, that is decided by the code. And then you have how many such pixels. The entire image is divided into 256 by 256. Okay, so this many pixels are there, and each pixel has some associated. So that is what we do in order to represent a digital image. So digital image, so you can see that the independent variables are discretized. In a digital image, the independent coordinates are discretized into pixels. Okay, that is the first thing. And then second thing is the grayscale which, or the grayscale value of each pixel is also discretized. Okay, so the entire image is basically divided into different segments, x and y, and each segment is called a pixel, and then each pixel is allowed to take only one of the grayscale here. Out of say if there are 256 levels of gray, then out of that you can choose, and that is a good enough good enough picture. This is a good enough picture, and therefore the size of the image. So in this above case here, what is the size of the image? Size of the image is 256 by 256 into 256. Okay. So that will that is why when you look at the camera of a phone, it will say 5 MB pixel. This is basically referring to how many pixels are there. So the total data or total number of bits here is, if you multiply these, you will get basically 16777,216 bits. So this much data is there in a picture like this. Now if it is a color signal, then what happens is that there will be 3 copies of this. One for, so let me just denote it here itself. So if it is a color signal, then you will have one more such, and then one more such. You can see. So for each pixel, so there is a corresponding representation in the. So this is say red. First one is say red. Then next one is green. Last one, sorry. So let me use. So this is red. Then green. Then blue. Okay, so there will be a blue intensity for the pixel. So if you take any pixel, it will have a red intensity. So which here the grayscale which I have shown, it is from bright to dark. Similarly, you can think about a red color. In one side it is like completely almost like white, and then it goes to red and more red, very dark red. So that way. So there could be 256 levels of redness, 256 levels of greenness, and 256 levels of blueness. And by mixing these independent RGB combinations, you can get any color. So if you take a computer screen or your mobile screen, you see all kind of colors coming out of it. That's because so there is a pixel which can be allotted with one of this. So in each pixel there is a red color. Say it could be due to an LED or LCD. Different technologies are there. I am not going into the technology part, but the image will have this format. So whatever is the data in the red will be given to the red LED, and then to the green LED is given by the second set, and to the blue LED it will be given from the third set. So each LED will glow, and a combination of these color will decide the pixel color. So each pixel has a minute color coming out, which is a combination of red, green and blue. Okay, and similarly for all the pixels. And if you have more pixel for a given area, then you have good clarity. So that is why, like when you go to say 16 megapixel camera, you have one clarity, and if you go to 100 megapixel, you have another clarity. So usually like 5 to 20 megapixels are common these days with a mobile camera, right? So that is the number of pixels that you have. So how many pixels along the x direction, how many pixels along the y direction, you take the product of it, and if it is coming in this megapixel, so that is the array size basically. And since it is a color image, you will have one such for red, another for green and another for blue. So is it clear? Your question is answered?
Yes, sir.
Okay.
Sir,
Yeah.
also, sir, the code that you have given here, sir, in grayscale code.
Yeah,
so
yeah.
Is it in BCD format, sir?
No, it is binary. I mean, if it is BCD means we will have only up to 100, right? So we usually use binary only for showing the. So I just put this comma, maybe a confusion. I just put just to know the number. It should be 8-bit.
Okay,
So,
sir.
yeah. So our eyes cannot really distinguish between the grayscale beyond this. See, if you look at two levels here between 1 and 2, the amount of change is very minute, because the entire bright to dark is divided into 256 levels, and if you take any two successive levels, it is very difficult for our eyes to distinguish between one from the other. Of course, we may be able to distinguish maybe some 50 levels across, maybe we will be able to distinguish, but between successive levels or they are almost the same, but slight difference in brightness. So that is one thing. So you can think about it as like the amount by which the LED will glow. So here it is completely off, and here it is completely on, and then you have 256 different levels of strength by which the LED will glow. So if it's a black and white, but if it is a color, it's you can think about it as a red light, and it is off and it is completely on, like that. So this is more than enough. There is no point in increasing the intensity levels beyond 256. You don't make much perceivable difference, but you can always increase the pixel size. That's what a better camera would do. because if you magnify an image, then if you still want clarity, then the only way possible is that you increase the pixels by which this image is represented. So instead of 256, if you go to say 1024, you have a better image. So then you have 1024 by 1024. So that is like 1 MB. So 1024 is like 1 kilo, right? And 1024 by 1024, you have 1 MB pixel. Okay, 1 megapixel. And then if you have more, even it is better. So you can still magnify this image and get very good clarity. Alright, so similar thing is for video also, same thing. Just only difference is that now these colors will change with respect to time. So, and that is what we call as frames. So you can think about these frames here. So a digital television, what is happening is that you display one image for some 1 by 60 of a second or 1 by 30 of a second, and then the next image will come after 1 by 30 of a second. So in 1 second at least 30 frames, that is very common. Or sometimes if it is a more better quality, then we will have 60 frames per second. Okay, so 30 to 60 frames per second will come in a second. So we are basically showing different images, and between two images there is hardly very small change. So we maybe if I can show a video. Video signal, so they are coming in frames like this. Okay, so they are coming in frame. So this is frame 1, 2, 3, say this may be like 60. So in 1 second you are changing the frames. So here maybe the guy may be standing like this. So in another picture, after 1 second, maybe instead of his hand here, he may be changing it to slightly a different position. So this will go slowly from frame by frame. So when you see 60 images one after the other coming like this, you feel it is moving, but other parts are remaining. So it's like just lifting the hand. So that's basically a perception of our visual system that is exploited in order to show a video signal. Okay, is that clear?
Yes, sir.
Yeah. So over and above whatever we said in the image, with respect to image, so all these are there in a video, but over and above we are introducing different pictures or different frames, they call it, with respect to time. So they are very closely related. Image and video, they are closely related. Okay, but for our course we are going to focus so much on 1D signal, which I said voltage varies with the time, or current varies with the time. So that type of signal, ECG signal, so that type of signal is what we are focusing on in this course. Now let's also define what is systems. What are systems? So systems take an input. So I am showing here like a block diagram. So this is a system. So it takes an input which is a signal. So this is an input signal. and then it gives you an output signal. So here I have taken time as the independent variable. So mostly if it's a 1D signal, mostly if you take a speech signal, speech is a most common 1D signal. Similarly voltage and current, another examples. So they are 1D signal, and so it will have some kind of amplitude variation with respect to time. So time is the independent variable in all these cases. So then we have an output signal. Okay, so we have an input signal and then we have an output signal. So what does the system do? The system will perform. So system could be represented by a transformation. This is basically doing a transformation. So whatever is the input that you give, it will take a transformation, and after the transformation you get a different signal. So you can say that y of t is basically a transformation of x of t. So this way you can, so by a system could be represented by an input-output relationship. Or another way, we can say the system transforms an input signal to get the output signal. So this could be represented like a input-output relationship. So y of t is actually a function of x of t, but how the functionality, that is decided by the transformation. Example. So y of t is equal to x of or x of t square. So whatever is the input that you give, it will just take the square. So that is the kind of transformation the system will do. Now why does it do something like this? I mean, that depends, like what we want to perform on the signal, depending upon what operation or what kind of changes that we want to make. Accordingly, we have to design the system. So system is used to manipulate or process the signal in order to enhance certain features or to compute certain quantities from the input signal and get an output. So this is an example. Y is equal to, or another very common example is basically this. This is basically an amplification. So basically what we are doing, we are taking a signal and just strengthening that signal. It's an amplifier. So here it is squaring, and here it is an amplification. Another example, after amplification you add some DC level to it. So if it's a voltage, X is a voltage, you amplify the voltage, and that means it is strengthened, and then you add some DC voltage to it. Okay. So various you can think about so many things, so many ways you can process it. Say you can have this also. Okay. You can think about infinite possible ways in which you can manipulate signals. A few more I will write. Say x of 2t, y of t is equal to x of minus t. Okay. But though I am writing so many systems, but whether all of these systems are possible to be made in the laboratory, so that is another thing that we need to look at. Not all systems which we write mathematically are possible to be made practically. Okay, so there are systems which cannot be made. So we will look at those things a little later. So sine of x of t, y of t is equal to sine of x of t, y of t is equal to x of t into sine omega t, y of t is equal to e raised to j x of t, etc., etc. Okay, so we can go on and on and on. So the examples of systems are plenty. So basically, what does it do? So there you can represent a system with an input-output relationship. So output depends on the input, but the input is going under some kind of transformation. Okay, so that transformation defines your system. All right. So now let me just go to topic back into the signal. Size of a signal. How big is a signal? Okay, how do we estimate the size of a signal? Now there are different types of signal, and size of the signal and the size of the type of the signal, they are in a way linked. So but let me define the size of a signal for a particular class of signal called energy signal. So we need to treat it separately, size of energy signal. Now, so what is the definition? The definition for energy of a signal x of t is defined as integral minus infinity to plus infinity modulus of x of t the whole square dt. So that is or the energy of a signal is defined by this formula. So you take the signal, take its modulus, then square it, and then integrate it from minus infinity to plus infinity with respect to time. Time is basically the independent variable. Okay, we are assuming time as the independent variable from here onwards, and we are only talking about one-dimensional signal. Okay, so under that assumption, we are defining energy of a signal is basically so it is an estimate of the size or the strength. If the signal is having high amplitude, it has large energy inside. So let's now why do I say energy signal? If this is finite, then we call it as energy signal. If E of x of t is finite, then x of t is called an energy signal. Okay, if it is infinite, that means if this integral doesn't converge, we are not able to evaluate and find the value of this integral because it is infinite, then it is no longer an energy signal. So that is why I said this formula is useful in finding the energy of a energy signal. So energy signals are those signals for which this integral will converge and give you a finite answer. So every signals you can't do this. So let's take an example. E raised to okay, let me write like this, x of t is equal to 0 for t less than 0, and it is equal to e raised to minus t for t greater than 0. So first thing is plotting this signal. How to plot this signal? So it has two parts to the definition. So this is our time. So t negative means to the left side of the origin. It is 0. It is mentioned that it is 0. And then for t positive, so this is 1, it is mentioned that it is t raised to minus t. So this is e raised to minus t. So this is the signal x of t. E raised to 0 is 1, so that is why it starts from 1 and then decays. And so what is the problem? Problem is to find the energy of the signal. So energy of the signal x of t is basically integral minus infinity to plus infinity x of t modulus square dt. That is energy of x of t is equal to, so we will divide it into two parts, minus infinity to 0, this is 0 dt, plus 0 to infinity, it is e raised to minus t modulus square. So the first term is 0, doesn't contribute anything, but the second term you can write it as 0 to infinity e raised to minus 2t. This quantity is positive, so whether you take modulus or not doesn't make any difference. So this is equal to e raised to minus 2t divided by minus 2 in integral. After integral we get like this, then you put the limit. So if you put the upper limit e raised to minus infinity, that is 0, and the lower limit e raised to 0, that is 1, divided by minus 2. So which is basically minus 1 by minus 2, and that is half. So this is the energy, or this is the strength. Okay, so we are basically using this formula to find the amount of strength inside the signal. Okay, another example, slightly different. X of t e raised to t for x less than 0, e raised to minus t for x greater than, sorry, not x, it is t. So t less than 0, this is the expression for t greater than 0. So let us plot this. So any signal, if you plot, you get an idea how. So this is x of t. Positive side is still the same, it's exponentially decreasing. So this is e raised to minus t for t greater than 0. For t less than 0, it is e raised to, so let me put minus e raised to t. Now e raised to t, if you look at it is something like a function that goes like this. Okay, it's a function that goes like this. But this is valid, this expression is valid only for t less than 0. So e raised to t for negative values of time, it is again decaying like this to the left side for negative values, because t become negative. So e raised to minus is basically, but now There is a minus sign here, so because of that it will be inverted like this. So this is basically minus e raised to t, and this is only valid for negative values of time. So you have negative values of time and positive values of time. For positive, your expression is e raised to minus t. For negative, your expression is minus e raised to t. Now the question is find energy. Find energy of x of t. So energy of x of t is equal to, so the formula is minus infinity to plus infinity. Take the modulus of x of t if you have negative values in this case, and then square it dt. So you split it because the functions are different. Minus infinity to 0, your function is minus e raised to minus t. You can just square because it is not a complex quantity. So by squaring itself, your sign will go away. Plus 0 to plus infinity e raised to, sorry, here it is plus. Then 0 to infinity, you have this. Now you see, from minus infinity to 0, you have this, so which is basically minus infinity to 0 e raised to 2t plus 0 to infinity e raised to minus 2t. Now if you do a transformation for the first integral, putting t equal to minus t or t equal to minus u, and then you will see that both terms are going to be same. So if you want, you can do that. If for this case, if you take u is equal to minus t, then dt is equal to minus du, and t is equal to minus u. So the first integral is going to become minus infinity to 0 e raised to minus 2u du with a minus sign because of this minus, which then you can, this minus and this integral limits you can exchange to make it plus, so it is 0 to so when t is equal to minus infinity, u become plus infinity. Okay, so it will be plus here. So let me just show that explicitly. So when t is equal to minus infinity, u is equal to plus infinity. T equal to 0, u is equal to 0. So that is why it will become plus. Now I am absorbing the minus and interchanging. So it is, okay, this is an integration variable. You can put t also. So that will be 0 to infinity e raised to minus 2t t. So now if you look at and compare with the second term, they are exactly the same. So you can write this as 2 times integral 0 to infinity e raised to minus 2t dt. Now this we have evaluated already, we got 1 by 2, so it is 2 into 1 by 2, which is 1. So that's the energy present in the given signal. So energy is what? Energy is basically the strength of the signal, how much it is away from 0, whether it is to the positive side or negative side. When we take the modulus, both will come to the positive side, and then we are integrating it with the square it and integrate it to infinity, from minus infinity. So it's the entire signal which is varying from minus infinity to plus infinity. How much is the strength present in it? This is like a measure of ability to do some work, the strength of the signal. So that is what we call as energy. So if you think about it as voltage, then the power or the energy dissipated in a resistor, we know that it is V square by R. So it is proportional to the strength is proportional to the square of the voltage. If you think of it as a current, then the energy dissipated in the resistor is I square R. Again, it is proportional to the square of the current. So that is why the definition has square in it, and then modulus is basically to incorporate the case of complex signal. So if you have complex signal also, you can use this. So we will take a break and we will come back after 5 to 6 minutes.